Hello, and thank you for joining us for today's webinar, where I'm going to help you better understand the growth responses of cotton crops when grown under tropical conditions. My name is Paul Grundy, and I'm with the Department of Primary Industries and the Australian Cotton Industries extension arm, CottonInfo. And I'm hoping that after this webinar, you will have a better understanding of the cotton plant's physiology and how it responds to tropical conditions, and that this will help you make better decisions as a crop manager in these environments. So to understand how cotton grows and how it interacts with a tropical environment, it really helps to be able to think like a cotton plant. But to be able to do this well does take a basic understanding of the physiology and true nature that underpins how a cotton plant grows. When I often give this presentation, I like asking the following question of participants as to which one of these crops grows more like cotton. Is it mangoes, maize, which we grow as a row crop, spanning about 5 months, similar period of time to cotton, or is cotton more like tomatoes? Most people, when I ask this question, nominate tomatoes, but in fact, the true nature of cotton is more closely aligned with that of a mango tree, in that it is a true perennial, and if left to its own devices, will grow consecutively year after year after year. And as we think about that true perennial nature of the cotton plant, it helps to then think about what does a cotton plant want out of life and how does that compare and contrast with what we want from that plant as human managers. And if we think about that cotton plant and what it wants out of life, the first thing it wants is eternal life. It is a perennial plant and its intent when it starts growing is to live forever. The second thing that it might want is to have babies, and that's the seed. And it wants those babies to be big and healthy, but it only wants to do this when the time is right. The third thing that it might want is the lint. And lint from a cotton plant's point of view is really just a bonus, useful for spreading the plant's genes along that riverbank in those environments where it evolved. If we contrast that with what humans want from cotton, the first thing that we want is lint, because that is the most valuable portion of the crop that we pick at the end of the season. And we're happy to accept the seed with that lint, but we want the seed to be small and we want to maximize the ratio of lint to seed as much as possible. And the third thing that we do as cotton managers is that we grow the crop as an annual so that the crop matures as early as possible, at which point we pick it and destroy the crop. And to give you an idea of the true nature of the cotton plant, this photo here is of some perennial plants that I've been looking at now for over about a 10-year period, growing in a drainage line. They are modern cotton varieties that have perenniated in that riparian area and have been growing there year after year. So that gives you an idea of the true nature of this plant that we grow. So one of the first things that I like to try and unpack for people is the concept of growth and development and differentiating between the two, because a lot of people can find this a little bit confusing. In this photo here, there's 3 different cotton plants that are sharing the exact same stage of development, which is first flower in this case. But you'll see that in each of those photos, despite being at first flower, there's very different rates of growth that has taken place up until that point. And this really goes to the heart of growth versus development. Development is a temperature-driven process that basically starts the minute the seed is in the ground and it imbibes moisture. The rate at which it emerges from the ground, the rate at which it produces nodes is driven by temperature, and that is development. However, the amount of growth that occurs whilst that development is taking place is something that we can manage as crop managers, whereas development is influenced by temperature. And you'd probably agree that when you look at these 3 different crop scenarios that are all at the same stage of first flower, that the growth of these 3 crops is very different. And that as crop managers, we would deal with each of these scenarios quite differently because of the difference in growth that's taken place. So when we look at that growth and development, it can be simplified into 3 basic phases. The first phase is the period that spans from when we sow the seed into the ground and it imbibes moisture through until when that first flower occurs on the main stem. And during this period, the plant is predominantly going to be growing leaves and stems and will start producing the buds, which we call squares. So if we look at the critical flowering stage of the crop, we can see that the crop is growing more stem, more leaf as the canopy expands, but it's also now putting growth into the development of bolls as those flowers are pollinated. And the filling of that fruit takes about 28% more energy, gram for gram, than what it takes for the plant to grow additional leaf. And there comes a point in this process where that bowl demand, that extra energy requirement to fill those bowls, reaches a point where the plant can no longer do both and the production of leaf and stem then ceases. And at that point, we arrive at phase 3, which is that post-cutout period. And from this point onwards, there's no additional new bowl set by the crop, but the crop is still growing as busily as ever, filling the bowls that have been set throughout the canopy. And ideally, this period really does need to coincide with good conditions. And as crop managers, we want to manage the crop in such a way that we're enabling that plant to continue to photosynthesize and feed those energy-intensive bowls as they develop. So as we go through those different crop stages, there's lots of different activities that we undertake as part of agronomic management. But one of the key inputs during each of those periods is the impact of climate and weather. And it's helpful to think about the weather from a cotton plant's point of view. We have sunlight, and what really matters is the intensity of that sunlight and the consistency of that sunlight in terms of avoiding cloudy weather, particularly during those flowering and fruit filling periods of phase 2 and 3. Temperature are really important. The optimal range is coolish nights that are between that 17, 18, 19 degrees overnight, followed by nice warm days that are around that 30 to 32 degrees during the day. So not too hot, not too cold. And then you've also got rainfall, which is not harmful in and of itself, but does create challenges for us in terms of managing nutrition, soil moisture availability for both rain-fed and irrigated crops, canopy management, and obviously rainfall has very clear implications for bowl opening and picking, as it can cause bowl rots or cause lint quality downgrades and disrupt picking operations. So one of the things to understand about tropical Australia compared to temperate regions is that the solar radiation in our tropical regions at the time of year that we're growing the crop is less than what it is in the south. If we look at when flowering commences in the south, it would occur just after the summer solstice, where you have long days and a very low incidence of cloudy weather. If we compare that though with when flowering commences for wet season sown crops that are sown December, January and February, flowering is commencing well after the summer solstice, and there's obviously the increased risk of monsoonal cloud blocking the sun's energy from reaching our crops. So in comparison to our southern environments, solar radiation is certainly much less in the north, and this is something that's often overlooked when we think about cotton production, primarily because cotton production in the south is a sun-soaked environment compared to tropical Australia. And to give you that comparison in another way, what I've done in this particular figure here is overlay the radiation that would occur at Moree, which is a very sunny, dry environment, with a number of different locations across northern Australia, and basically overlapped the type of radiation that you would expect. So this is mean daily solar radiation, and how it would intersect with the crop's reproductive period, whether it's planted in October at Moree or planted in mid-December in northern Australia. And you can see, compared to the dotted line there, that there is significantly less radiation available to that crop during that crop's reproductive period, which has implications for how we might manage the crop. So the reason why sunlight is so important is that cotton's growth is really a process of energy transformation, where solar radiation is incepted by the leaves and it's converted through that growth into seed cotton. And lent yield, when you think about it, is really the sum of a set of parts, being the total radiation that's available within a given environment, how much of that radiation is intercepted by the leaves of the crop's canopy. Then there's the efficiency at which that intercepted sunlight is converted through photosynthesis into assimilates and sugars and things that the plant can build those parts with. And then you've got the proportion of the dry matter or the growth that's produced and how much of that is directed into seed cotton as opposed to other fractions such as stem and leaf. And as managers and plant breeders, we have a lot of control over most of the parts of that equation. But one thing that's more difficult to control is how much sunlight we might achieve beyond selecting a time of year where we might hope to increase that exposure, but we can't help cloudy weather when it does occur. And then when we think about the growth that takes place, we can think about that growth in terms of the radiation use efficiency of the crop. And what this basically is a measure of is, if we imagine a solar panel and there's a given amount of sunlight falling on that solar panel, radiation use efficiency is a measure of how much electricity is coming out of the back of that panel. And if we look at crops such as sugar and maize, they have C4 photosynthesis, and they're growing what we would describe as a low energy product, so carbohydrate based product. And they basically produce 2 grams of biomass for every megajoule of photosynthetically active radiation that the crop intercepts. We then have crops such as rice and wheat that have C3 photosynthesis, the same as cotton, also connected to lower energy products, and they have a lower radiation use efficiency, but again, they produce about 1.4 grams of growth or biomass for each megajoule of sunlight intercepted. And then you look at crops such as soybean, cotton, and mung beans. C3 photosynthesis can only produce 1 gram of biomass in proportion to each megajoule of photosynthetically active radiation that they receive. But we're then directing that growth into a high energy product in the case of legumes that are high in oil and protein, and cotton in the form of that cottonseed that's high in oil. So what this means is that we basically have a prerequisite if we want to achieve high cotton yields, that we need prolonged periods of high radiation where we're maximizing the interception of that sunlight by the crop canopy, particularly during that bulb filling period. And that brings me to the topic of shedding, which is a natural response when these crops are exposed to low light conditions. The mechanics of shedding are driven by degenerative enzymes that cause that fruiting structure to detach and shed. And ethylene is the key promoter of this process, with this compound increasing within the plant, either when there's inadequate organic nutrient supply or some sort of injury associated with insect damage or from disease. So if we look at inadequate nutrient supply, and what does that actually mean? Essentially, this arises when we either have impeded photosynthesis, so something's reducing the efficacy of the solar panels of the crop, the leaves, or it can also arise when you've got competition for assimilate within the plant. And this is generally when you've got a developing boll load and the energy demand of that boll load exceeds the ability of the crop's canopy to supply those nutrients. And in each case, that results in deficient supply. And if we look at those environmental factors that might disrupt photosynthesis, for example, the obvious one is cloudy weather, but also high temperatures, either during the day or at night time, can disrupt that photosynthetic respirational processes, basically reducing the net amount of assimilate available for growth. Clearly, drought conditions can reduce the plant's ability to keep the leaves at an optimum temperature for photosynthesis, and similarly waterlogging can as well. So each of these environmental factors can affect that leaf function. So I want to delve a little bit more deeply now into the relationship between radiation and yield and how that might relate to shedding. And the first comment I'd make is that the relationship is complex. During the period that we conducted research in the Burdekin over 5 years, we tried to establish a relationship between yield and cloudiness. And this figure here shows the relationship between lint yield and mean daily radiation that occurred during the flowering period, in this case around 4 to 6 weeks for these different crops. And what you can see here is that radiation, as it declined by each megajoule on average during that flowering period, we lost 235 kilograms of lint, so just over a bale, as that radiation declined per megajoule. However, this relationship only explains about 40% of what was going on. So there are other factors that contributed to that relationship. So radiation is just one part of the story. So the reason for that complexity is that when fruit is lost, particularly during early to middle flowering, that shedding can be followed by compensation. And what you can see in this slide here is 2 examples of crops that have been grown in the same season but were sown at different times. The top crop pictured there is a crop that was sown in January, and by the time it started flowering, sunny conditions had returned in early March. And that crop has got a more regular distribution of bolls from those lower early flowering fruiting branches through to the uppermost late flowering fruiting branches. And if we contrast that with the crop underneath, that crop was planted in early December and it experienced monsoonal, wet, cloudy, overcast conditions for several weeks during early to middle flowering. And you can see that the distribution of bolls in that crop is quite different, with shedding having taken place in the lower canopy and then those positions being compensated for in the upper canopy. And that's reflected in that figure there, where the majority of bolls were retained on those late flowering fruiting branches. And these 2 treatments yielded exactly the same yield at 11.5 bales per hectare, but the distribution of bolls within that canopy was quite different in response to that cloud-related shedding during early flowering. So in addition to cloudy weather, high temperatures can also result in fruit shedding. Hot nights that are 24 degrees and above, and days where the daytime maximum reaches 35 or above can both act together to reduce assimilate production and cause overnight respiration losses. These temperatures can also directly damage the development of pollen and the ovule, and the result can be either boll shedding or the boll becomes parrot-beaked because of uneven pollination throughout the boll locules. Often when we see fruit shedding associated with heat damage, it presents in a fairly structured way within the plant. And what you'll notice is that fruiting structures of the same physiological age throughout the canopy, so they might be in different locations, will all shed and desiccate together. The shed bolls will often be partly retained on the plant, and we call that phenomenon boll dangle. And one of the things that often goes hand in hand with high temperatures in our tropical regions is high humidity, which can limit the plant's ability to efficiently transpire moisture through the leaves and keep those leaves cool. When we think about rainfall and how it might affect the cotton plant, generally speaking, it doesn't directly affect the plant, but it can affect the way in which it grows, and it can certainly affect bolls as they begin to open. If we think about how it affects root system development, if the soil becomes wet for an extended period of time, which reduces the availability of oxygen in that soil, the roots of the cotton plant will tend to grow more actively in those upper, more oxygenated layers, resulting in a crop where most of its root system is confined to that first 10 to 20 centimetres of soil, which has implications for when the wet season finishes and when we might commence irrigation, or how long a crop might hold on and use the rest of the soil moisture profile. Similarly, rainfall during squaring and flowering and fruit setting doesn't do a lot of damage to the crop, but once those bolls mature and begin to open, rainfall on opening bolls can have devastating impacts, as you can see in that picture there, causing boll rots or tight locking where the lint in that open boll fails to unfurl and they end up looking like little mandarin quarters and they're not available for picking. In terms of the impacts on the root system, this is concerning to a lot of people because in our temperate environments, we're used to seeing cotton develop strong, healthy taproots that penetrate at significant depth in the soil profile. And I had the opportunity to travel to Brazil a couple of years ago, and wherever I went on farm, I asked permission to pull a plant out so I could have a look at its roots. And I would ask the growers that we were visiting, did this root system look normal? And in fact, they used to answer me and say, what is not normal about that? And what this confirmed to me, and again in their system, where it's a wet season production system, is that when those lower layers of soil remain wet for an extended period of time, that a normal response of cotton is to restrict its growth to those upper soil layers. So whilst roots may be confined to those upper layers during wetter than average seasons, no two seasons are the same, and in drier than average conditions, roots can penetrate to depth, and also roots can recommence growing into those deeper areas of the soil profile once those waterlogged conditions recede. And we've found in a number of situations in Northern Australia where roots have been able to penetrate as deep as 2.5 metres from the surface on particular soil types as those crops have been searching for water and nutrients. Therefore, it really helps to have an understanding of where the roots are because that can inform both your irrigation, if you're irrigating the crop, or nutrient management. So hopefully that provides you with a bit of insight as to how climate is interacting with the cotton plant and how it grows. And that then brings about the next question is, how do we plan for these climatic risks? How do we plan for those interactions so that we can make better decisions as agronomists managing these crops? And really the best place to start is to look at the climatic records for your particular region, paying particular attention to the profile for radiation, rainfall and temperature patterns, which we can then use to inform agronomic management in terms of planning for what is likely to occur and when. When looking at climatic data, it's much more informative to look at median data compared to means. This is because those large singular events, particularly with things such as rainfall, can really cause mean data to be skewed. Fortnightly data, if it's available, is more instructive than monthly data. And if we think about how quickly these crops grow, and it is rapid under tropical conditions, and often how quickly conditions can change, particularly in the transition from the dry season to the wet season and then the wet season back to the dry season, fortnightly data can be much more informative. And the other thing that's informative, as well as looking at the median, is to also look at the variability associated with that median. So that is looking at the bottom 10% of years for that variable or the top 10% of years, as that can give you critical insights as to the range that you might expect in some seasons around those different parameters. And those records may give us an idea of what the climatic challenges may be for a given environment that we can then use to better plan some of our operations. For example, time of sowing is a powerful tool that we can use to try and place key crop development stages at a time of the season where we're likely to intersect the best conditions available for that growth and development. Similarly, we've got irrigation if it's available to us, the use of nutrition, and plant growth hormone regulators such as mepicot chloride that, again, we can use to manipulate the growth of the crop and aim to make the best available use of those resources in that given environment and effectively manage growth and development so that we're hopefully partitioning as much of that growth as we can into pickable lint yield. So if we look at sowing time, which I would argue is the most powerful tool available to us to manage climatic risk in Northern Australia, the primary objective of selecting a sowing time is to, as best we can, offset key climatic risks, which will vary for different locations and for different soil types. The key risks to consider when we're thinking about sowing time is obviously crop establishment conditions, and the things we might be concerned about there is excessive heat or the influence of rainfall that may stop us being able to traffic fields and get seeds into the ground. And then we've got those subsequent conditions after we've successfully planted and established that young plant. Essentially, how does that sowing time, keeping in mind that development is controlled by temperature, so when we put a seed in the ground in Northern Australia during the wet season, we can just about assume that 45 to 55 days later, that crop will begin flowering and then bowl filling. What sort of radiation or temperature envelope are we exposing that crop to? And then subsequent to that, what sort of conditions will we experience, hopefully dry conditions, for bowl opening and picking? So to give you an idea of how you might be able to practically use long-term weather records, in collaboration with Quaffy and Joe Eyre at the University of Queensland, we've come up with a little program that you can use to basically select your location and look at the climate records most relevant to that site from the Silo database as median data in fortnightly intervals. That QR code in the top right-hand side will take you to this program and you can run this for yourself for your location. That program will give you an output that looks a bit like this. And I'm going to unpack the ORD just as an example for how you might interpret this climatic record data that's presented in these figures. The first thing that you can see in these figures is the median value for maximum temperature indicated by that thick red line per fortnight throughout the year. And the shaded red zone both above and below that line and where that finishes represents the hottest 10% of years and the coolest 10% of years in that range. So it gives you an idea of the variability of temperatures around that median value. Similarly, if we look at radiation, so we've spent a lot of time talking about radiation in this presentation, you can see a median value for fortnightly radiation by that solid black line, and the dotted lines either side of that show you the sunniest 10% of years and the cloudiest 10% of years. And the thing that you'll notice for the ORD environment, as you would expect as rainfall reaches its peak in late January and early February, that in some years, median daily radiation can be very low, being around 10 megajoules per fortnight. And you can see that there's more variability on the bottom half of that equation than the top half. If we look at rainfall itself, you can see there the median fortnightly values for rainfall that will occur in that environment. But again, you can look at the top 10% of years and the driest 10% of years, and you can see that even in the driest 10% of years, there's at least some rainfall could be expected for this environment. And the wettest 10% of years, it can be clearly quite wet. So you can imagine that trying to plant seeds in the ground in late January and early February, you would expect to be challenging more often than not. And then if we look at minimum temperatures in this environment, again, presented in the same way as maximum temperatures, and you can see that by mid-July, median temperatures fall away. And whilst the median is still warm enough for the crop to continue developing and growing, you can see that there's a percentage of years there where those temperatures fall below 12 degrees and would be problematic for crop growth and development. And then finally, if we look at those climate parameters and then think about where might we best be flowering and filling bowls, you can see across that 12-month period, and assuming that we're planting during the wet season, which is the Bollgard 3 planting window, that there's an ideal window of time that commences in late March and runs through to early June, where we have really good radiation, mild overnight temperatures, and milder days that would be optimal for flowering and bulb fill. And similarly, there's a shorter period that shares a similar spread of temperature and radiation values from mid-August through till about early October. So if we think about that figure that we just looked at and think about for the cutting environment, when might you sow to optimize production? And clearly mid-February sowing would best avoid those climatic risks, being cloudiness, hot nights, hot days, rainfall, for the flowering, bowl filling and bowl opening period. This is because sowing in mid-February is going to result in crops that commence flowering in late March. So as we come into that really nice period of weather during April, May and early June, so that would best coincide that bowl setting and filling period with those optimal conditions and minimize the frequency and severity of fruit shedding or unfavorable canopy responses. However, sowing at this time comes with a really high risk of not being able to sow at all. So if you put all of your eggs in the basket of sowing in mid-February, particularly with the clay soil types in the Kununurra region, it'd be fair to say that more often than not, you would be unable to plant at this particular point in time, which basically means that for this environment, despite middle of February being optimal in terms of coinciding flowering and bowl fill with the best conditions later on, that you're going to need a staggered approach where you're going to have to address that risk of being able to plant at all by commencing sowing in early January if conditions are available. And then you might have a staggered approach where you try and plant consecutively during that January, February and March planting window to ensure that you do get some crop in the ground. And clearly, crops sown in January as opposed to February and also crops sown in March will intersect those conditions later in the season a bit differently. And we can see that in this example here. So if we look at crops sown at the beginning of the window in early January, those crops will commence flowering from mid-February. And these crops will be challenging to manage because during that February period, when the crops start moving towards flowering and that canopy is becoming well developed, there will be a high risk of expansive canopy development and clearly a risk of extensive fruit shedding during this period. However, this risk is partly offset in that we have sufficient season length through until early June to compensate for those losses and essentially grow a top crop to compensate for that lower canopy fruit loss. So again, if you think about the growing strategies that you might use, the strategy will be different for an early January sown crop as opposed to a mid-February sown crop, for example. If we look at the other end of the sowing window as a comparison, and that is sowing in March, so assuming that January was wet and February is wet, which will happen in the Ord environment in some seasons, but it finally dried out in March and we're able to sow in March, you can see that those crops sown in March are not going to flower until we get towards mid-April or a bit later. And that period of time that we need, so we ideally want about 2.5, 3 months of time to set a large number of bowls and fill those bowls, is going to overlap and run into that July period where, depending on the season, in some years you're going to run into exceedingly cool conditions that are really going to slow down and impede that crop's ability to fill bowls during that time and may in fact really limit the potential yield of these crops sown at that time in some seasons. Now, keeping in mind there is that opportunity to keep these crops ticking along. So again, your management is going to be quite different for this particular situation, and perhaps set some compensatory fruit in that mid-August to early September period, provided that that can be matured in time for picking and crop destruction by the middle of October. But you can see in this example, in that 3-month planting window that might be available in the Ord, when you sow is going to have significant implications for how that crop might be managed and how that crop will intersect weather conditions based on what we know from long-term climatic averages. So I'm hoping this webinar today has helped you to better understand how the cotton plant grows, particularly in response to climatic variables, and will help you to think a bit more like a plant so that you can read the crop that is in front of you, understand what it's doing, and importantly, be able to anticipate what it might be going to do next so that we can respond appropriately as plant managers. And in thinking like a plant, be able to appreciate where that crop is at, think about what conditions it's been exposed to up until that point, what are the conditions likely to be in the near future, and how do we think that crop might react so that we can then work with that plant or sometimes against that plant in order to get what we want from it as cotton managers. And that clearly is a high yield of lint that comes with the seed at the end of the season. So in finishing up today, I'd just really like to acknowledge a number of growers who have hosted research work for myself and other colleagues throughout Northern Australia's regions, which over many years has given us a very good understanding of a whole range of parameters that are relevant to cotton production in the tropics. Really like to call out and thank a great colleague of mine, Dr. Stephen Yates with the CSIRO. He's retired now. Steve has been a fantastic mentor for me and has done so much work in this space. So I really just want to acknowledge his input into the talk that I've been able to give today. There's been a number of technical staff across a lot of organisations that we've worked with that have made a tremendous contribution to the research that's taken place, and also want to acknowledge our industry collaborators, CSD and Bayer, across various projects. Much of this research has been funded by Cotton Research and Development Corporation and various CRCs over about 15 to 20 years, and currently is ongoing through the CRC for Developing Northern Australia. Thank you. I hope this webinar has been helpful today, and until next time, goodbye.